Okay, last video of the entire term. Oh my gosh, this is sort of a lot. Actually, to be honest, I'm going to record some video discussion of some of the sample exam problems as well, but this is the last content that is related to specifically your exam for the final. And be sure to, by Thursday at noon, fill out the survey, which is essentially getting you mini quiz points related to the reading. And tell me whether you are likely going to want to take the truncated final exam on just chapters 11 and 12, in which case there is a weighting for that, or a different course weighting for the final exam if you take the comprehensive final exam. What I'll probably be doing is having you take the comprehensive final exam, which is the earlier bits, and then also the test that the people who take just the fourth midterm would take. So you'll, if you want to do the comprehensive exam to raise your grade because you now know the earlier material better, that's easy to do. You just take 2 tests and you could take a break in between them. So that's sort of a nice convenient feature. Doesn't have to be all at once. So look at the wording there carefully and then answer that question by Thursday about noon. Okay, so if I were to give you a slope and an intercept, we have the notion that B1 is the slope in the sample, and it's estimating an unknown population characteristic beta 1. Again, my truth is the following. We're assuming the following. Yi is beta 0 plus beta 1 xi plus epsilon I. We'll discuss in the next video exactly the nature of this, but you can see beta 1 is a slope of the population, and B1 is the sample slope. Okay, so we got the actual population slope, beta 1, and the sample slope, B1. Well, my claim is it's going to be higher or lower in terms of its precision, and the standard error measures that precision. So the 3 things that impact the equation for the standard error are the spread around the trend line, which we call S sub E, the spread of the x's, and the number of data points. Like before, you sort of think, oh, of course, more data, more precision. Let me convince you of that. If there are 2 possibilities for sampling from the same population distribution, you're maybe thinking heights, x, and weights, y. If there is a beta 1 as a slope, and there's some scatter around the trend line, and that's a lot of data here, or a little bit of data. Now, with a lot of data, my thought is you could estimate quite precisely the truth. Your sample slope may be a little bit off, but with a small amount of data, your sample slope might be quite a bit off. The illustration here is meant to suggest more data, smaller standard error in the slope. Our slope is more precisely estimating the unknown population trendline slope. Let's go after the spread of the x's next. My claim is, again, in 2 different identical populations, again, maybe heights and weights, would you rather, when looking at the relationship between height and weight, would you rather have all your data in the 5'7" range, all the people who claim to be 5'7", or, and so 10 data points there, 10, or would you rather have 10 data points spread throughout the ranges of heights? My thought again is if you were to show me the data, it's going to be a lot more precisely estimated with a sample with a greater spread of the x's than with all the data in a very narrow range of the x's where the slope could even be negative because we're only limiting ourselves to a very narrow range of the x's. The line that best goes through the graph here could easily have a slope that's far off of the truth. Okay, so more data is good, more spread in the x's is good. And here's a quick little hint. If you're designing an experiment to look at the relationship between x and y, if you can't afford a large sample size, a large n, you can always make sure you choose x's that are far apart from each other, some very low and some very high, to give you the level of precision that you want. Finally, the role of S sub E. That's again the numerator term. And again, I'm going to give you two situations. Now they're not the same, but imagine the same exact slope in the two populations. Would you rather have the data tightly around the trend line or widely spread around that trend line? Again, small standard deviation of the residuals, very narrow versus quite wide. My thought is with the narrow distribution of the y's relative to any given x, I can probably pretty precisely estimate the slope, whereas here, just due to a couple data points being wrong, not representing the overall trend, we could misunderstand the relationship between x and y. So these are the components of the standard error for a population slope based on the sample slope. So now that we've seen the composition of this, you could calculate one by hand, but I could also show you where in JMP output you could find that relationship. Now let's go with the corn yield and the rainfall data. If I were to try and show you a trend line, here's the trend line that we looked at earlier. Fit a line. Down near the bottom, you can see the following, and this is the sort of output that I could give you in the final exam. Notice that the intercept is labeled as such. It's 23.55 bushels. If there's no rainfall at all, you get 23.55 bushels of corn. But for each inch of rainfall, you go up a 0.7755 bushels. 1 inch of rainfall buys you an extra 3/4 of a bushel of corn. The standard error, that is SEB1. B1 itself is the estimate. So if you are given these two values, you could do a hypothesis test relatively easily, or heck, if you are given all of the output here, you are given this test statistic T that we're about to describe, and even then the p-value. If for whatever reason you were to have those values obscured from your data, you could still tackle the problem. So if I were to say pretend that you have no information about those two bits of information. Let's go with that. Suppose you knew none of that. My claim is from just the slope and just the standard error, we could get to a test statistic T and then the p-value. So let's see how that could occur. Okay, so I'm going to move these over here off to the side. Oh, it's a simple matter. All we have to do is to compare our data, if you will, in this case, the slope in our sample to what hypothetically it should be if the null were true. And if the null hypothesis of no relationship is true, we're going to compare our sample slope to 0. and divide through by a standard error. That looks just like a t-table from before. The only difference is n minus 2 degrees of freedom. Okay, so in our case, we had our sample slope was, trying to show you exactly the sample slope, 0.7755, 0.7755 minus 0, again compared to the null hypothetical case, and divide through by now our friend, the standard error, 0.2938, 0.2938, 0.2938. And if I got my calculation right, hold on, you try this at home, 2.8 in value. Okay, let's verify that we got 2. No, I lied. 2.6. Shoot, I was thinking I could remember that and I blew it. Okay, 2.64. So just verify that you get 2.64. And all you got to do is, given the intercept and slope, the hypothetical possibility of no relationship, you've got a slope to compare to that null relationship hypothetical. If I've got a 2.64 with the t-table, you could look up that value. And you could say 2.64 and up, or negative 2.64 and down. But you get that for free. JMP will do it for you if you look carefully enough. Okay, maybe a couple more things. A confidence interval for the slope, same as before. Estimate plus or minus 2 standard errors, okay? Where I guess the value of t, alpha, is based on 95% confidence overall and n minus 2 degrees of freedom. Okay, so let's go ahead and try that with our corn yield and rainfall data. And I'm going to move this over here so that way we can't see anything other than the estimate and the slope. I'd say 0.7755 plus or minus, well, the t value will appear here, times 0.2939, times 0.2939. The t value that I will be using is based on degrees of freedom equal to 36, because we've got 38 data points in the data set, 36 degrees of freedom. So let me get you the t value for 36 degrees of freedom appropriately. So I happen to have a t-table in front of me that has exactly 36 degrees of freedom. And so I'm going to go ahead and use that. You should get one that's close if you don't have exactly 36 degrees of freedom. You should probably use 35 or 30 degrees of freedom and have that row. So I got 2.028. 2.028. And so now working with that, going to multiply that by the standard error, 0.2939. And I get 0.5960. So 0.7755 plus or minus 0.5960. That's sort of a wide range, a wide margin of error, 0.5960. So on average, for each extra inch of rainfall, we get about 3/4 of an additional bushel, plus or minus 60% of a bushel. That could be as low as 0.17 of a bushel, as much as 1.37 of a bushel. Does it seem like more data would be appropriate? If you're thinking to yourself, duh, you're thinking along the right lines. Yes, more data will get you more precision. Okay, let's verify that that is the case. Seems pretty straightforward, because if we were to go back a little bit, we could see the equation says more data gets you more precision. My bet is you could even probably solve for the target standard error you want. If you have a standard deviation of the x's so far, that's a standard deviation of the rainfall values historically. If you know the spread around the line, maybe algebraically, you could solve for how many years worth of data you need to get the desired level of precision. That's not an exercise I'm going to be doing for you right now, but it is pretty easy. Directional alternatives. Like with a t-test, we could choose to go with a directional alternative. It's really pretty easy. Simply say to yourself, take that two-tailed p-value and cut it in half. If the data matches your trend, if you are asking yourself, do plants grow over time? Okay, you're sort of thinking that's going to be an obvious yes. Do the roots grow over time? Again, an obvious yes. That's the natural biological or crops question. Do we have growth in the plants over time? My p-value for my hypothesis test is less than 0.0001. But if I was doing directional, the alternative hypothesis being that the slope is positive, I would cut this p-value 0.0001 in half. My p-value then is less than 0.00005. Still, I reject the null hypothesis, but if you naturally have an alternative hypothesis that is directional, it's easy to go for taking the p-value and cutting in half. Okay, so lastly, here's what we need to believe is true for us to trust the linear model, okay? And I tend to think about this in terms of x equals the height and y equals the weight of a person, okay? So let's first off look at the bulk of the trend relationship. That's linear. It says the average weight for a given x follows a linear trend line. But from person to person to person, there's variability around the trend line. Not everyone that's 5'9" weighs exactly the same. There is an average weight of people who are 5'9", but then some people have a positive epsilon. They are heavier than average for 5'9" individuals. Other people have a negative epsilon. They are lighter than average for 5'9" individuals. So conceptually, the actual weight is the average trend plus how far off the trend line each individual is. And if this is a reasonable description of the population, and where knowing my neighbor David across the street's epsilon doesn't help you predict my other neighbor uphill from me, Sherman's epsilon, you have epsilons that don't depend on each other. So if you can imagine a situation where knowing one epsilon helps me predict another one, you shouldn't be using the linear model in that case. Basically think an independent sample will get you this. If the 5th data point doesn't help you predict the 9th or the 27th or the 53rd, you have independent sampling, you've achieved the first condition. Second, the epsilons don't tend to be larger or smaller for x's that are larger or smaller. There's no systematic trend for epsilons to be positive for certain x's and negative for others. Indeed, that's another way of saying there's no curve in the data. It's really hard to see that, but if systematically we see the trend line like that, okay, but we fit a straight line trend, supposing we had a very tight spread of the data around the the curved trend, you can see the errors around the linear fit would all be positive in the middling range, but negative in the lower and the upper values for X. A curve doesn't fit a straight line. Okay, so this is another way of saying not curved. Third, the epsilons must themselves be normal with a mean of 0. That's easy. Mean of 0 is achieved by the second condition. Common standard deviation. So in other words, if I were to go up and down, again, a root mean square error. So again, going up and down 2s sub e, it's going to capture all of the data because the standard deviation is relatively constant. A data set like this, where the data spread widely apart for large x's, but small spread for small x's, not okay. And then lastly, normality in the population. To get after normality in the population, I want to consider the thing that I will term a residual. Here's our model. I'm going to write the model over here. Y is beta 0 plus beta 1x plus epsilon. Yi is beta 0 plus beta 1 xi plus epsilon I. And I'm going to fit a model here that I'm showing now in blue. Y hat I is b0 plus b1 times xi. That's my trend line. And if I subtract the second equation from the first one, I will have what we term a residual. E sub I is yi minus yi hat. How far vertically are the data points away from the trend line? How far away is an individual's weight from their predicted weight, if you will? That's going to be, algebraically, I'm going to collect like terms, beta 0 minus b0 plus then beta 1 minus b1 times xi plus epsilon I. And here's a nice thing. If we have any good degree of precision at all, that's going to be approximately 0. The sample slope will be quite close to the population slope. Similarly, the intercept in the sample should be approximately equal to the intercept in the population. And so what we have is that whole thing zeroes out, and the residuals should be approximately equal to epsilon I. So if I were to look at these residuals, which have that definition here, I could check normality in the residuals. Do we see a bell curve? Or chapter 4, section 4, if I used a normal probability plot, a normal quantile plot, could I see approximate normality? If that is the case, I'm happy as a clam, because then I'd be able to use, if all three of these conditions hold, I would be able to feel comfortable using regression, and I'd feel comfortable testing a hypothesis about a correlation. These are the underlying conditions for linear regression and correlation to be assessed and tested via the regular procedure. Okay, so boom, I just said that. We're good to go. Last thing I want to mention is, by way of review, the slides online are a list of things that I typically go through and things you should check off. Do you know that the way you collect data is important? Can you calculate things like a histogram? Show me one. Can you calculate an X bar, a standard deviation, etc.? If you go through each of these little slides in the rest of this lecture notes, you should be well versed in what you do know and what you don't yet know would want to study for the final exam, supposing you're doing the comprehensive. Again, if you're choosing the shorter version of the final exam, it's not comprehensive. It's going to be just on chapters 11 and 12. Okay, I'm tired of talking. You're tired of listening. Get to studying. We'll see you soon.
Bye-bye.